algorithms, and it's actually quite controversial. I saw that in the open review, you actually got 2 very strong accept.
People found if I use vanilla GRPO for optimization, we will have very weird response length behavior. So for Docker GRPO, what we do is very simple. We just want to go back to the very basic but correct formulation of policy gradient.
What do you think would be the most important problems for large language model training? I want 2 answers. One is for the next 1 year, another is for the next 10 years.
I think for me, very important problem is to creating.
Today, I have the chance to talk with Dr. Zichen Liu, one of the top AI researchers working on large language model training, specifically reinforcement learning. One of his work demonstrates that the well-known GRPO training algorithm that powers DeepSeek is actually flawed. A few months ago, he published another paper uncovered the fundamental flaw in the floating point precision used by most of the reinforcement learning frameworks, and it causes quite a buzz. Even Andrej Karpathy highlighted these works on Twitter. We'll talk about all of his experiences and thoughts in this field. Welcome to the podcast. You are one of the top AI researchers. Do you mind give us a quick introduction and what motivates you to the domain of reinforcement learning?
Yeah. Hi, Zachary, for the invitation. I'm very happy to be here. I'm currently a final year PhD student in Singapore, and also I'm a research engineer at CAI lab in Singapore. And during my past 4 years of PhD study, I started it from the deep reinforcement learning, classical deep reinforcement learning, like focus on playing Atari games, Wojoko simulation kind of stuff. And then later I switched to LLM post-training because I found LLM post-training is a quite successful application of RL, and it can create a big impact in the AI fields moving forward. So that's why I choose to work on reinforcement learning for.
That's amazing. Let's jump right into your most recent works that are quite influential. So let's start with the paper, Understanding R1 Zero-like Training, a critical perspective. In this paper, you talk about the theoretical issues within the popular GRPO algorithm, and it's actually quite controversial. I saw that in the open review, you actually got 2 very strong accept, which is quite rare in the AI conferences. So do you mind just share with us a big backstory of this paper?
Oh yeah, sure. Actually, we worked on this paper back in January of this year, which is the birth of the very famous DeepSeek R1 paper. Right after DeepSeek R1, actually, in the meantime, we are working on RLVR for mathematical solving concurrently of DeepSeek R1. But immediately after its release, we read their paper and we found some of the intuitions they bring and also some of the findings they have. We have some misagreement with them, typically, especially for the aha moment and for the phenomenon where as training goes, the response length keep increasing. So these 2 phenomena to us is quite abnormal at that time. So we decided to investigate why this happens. And that leads us to the finding where we found there's actually no aha moment during RL courses because the base model itself can already exhibit the self-reflection, self-verification behavior. And also that also leads us to the finding where we found GRPO might have some length bias or question difficulty bias, which can lead to this ever-increasing response length phenomenon, which is reported by DeepSeek R1 paper.
Yeah, that's amazing. Could you, for the sake of the audience, could we just walk through the GRPO algorithm step by step so we can get on the same page of the problem?
Oh, yeah, sure. So I'll use these slides for illustration. So basically, GRPO is a simplified policy gradient RL algorithm, typically for LLM RL post-training. And for any question or any prompt, we would like to sample a group of responses, and we would like to grade each of the response with a reward scalar. Typically, it's a binary scalar, say 1 or 0 for the correctness. And sometimes we may introduce some format reward as well. And then we will normalize among this group to calculate the advantage. And finally, we will use the advantage to do the policy gradient estimation and use that policy gradient to update the whole LM parameters.
Do you mind walk through the different components of the GRPO algorithms? I saw that the GRPO algorithms has 2 summations. Do you mind just give us a very high-level intuition on what each part of the algorithm is doing?
Oh yeah, sure. So looking at here, this equation, so this capital G is actually the group size. So that means for each question, how many responses we would like to sample. And this first summation is over these responses. And then the second summation is over each token of each response. So here from T2 equals to 1 to the length of that response, we would like to sum up all the tokens, all the losses on each token times the for that response, and then divided by the response length in the front. But actually, as we will see later, this is one bias that GRPO has, which we call length bias.
So could you just step very back on what is policy gradients? What is that organizing for? And I think policy gradients precedes all the GRPO, PPO. So maybe let's just go to the very basic here. What's policy gradient?
Yeah, sure. So policy gradient is a type of our algorithm which is to optimize your policy towards maximizing the cumulative reward. So basically, you would like to, given a observation, you would like to take some action. And this action got some probabilities. And after you take this action in the environment, you will receive some reward. And then you will adjust the probability of taking this action to increase that reward or to minimize the negative reward. So that is basically to adjust the probabilities of your action towards maximizing the total rewards.
And how does that action reward observation translates into large language model, say it is trying to solve a math problem?
So in large language model context, the observation we have is the question we give to the LLM, and then the action is the response and return us. Then the reward will be how good is the response. Typically, for example, for mathematical problem, it is how correct the final answer towards the question.
So could you help us walk through the raw formula for the policy gradient? What does the loss function and the gradients mean? Maybe that will help us transition better to the difference between GRPO and Dr. GRPO.
Yeah, sure. So actually, if we denote pi theta as the policy, then the policy gradient will look like this. So basically, we will sample trajectories from this pi theta policy, and we take expectation over these trajectories. And for each trajectory, we will have a sequence of state action, state reward, state action reward, and so on, which denoted as E, AT, and then RT. RT is not visible here because RT eventually will be converted into the advantage estimation, which is denoted as A here. So basically, we will have this action probability pi theta given ST, and then we will have its advantage estimation AT. And what we do for policy gradient is to just reweight the log probability of the action with their advantage, and we convert it into as the gradient of the model parameters to be updated. And note here that over the horizon of this trajectory, which is the capital T, we do the summation over all the time steps instead of the average, which is kind of a hint why GRPO is biased.
Amazing. Could you go through the formula for GRPO and Dr. GRPO?
Yeah, sure. So these two formulas looks a little bit complex compared to the previous one because we also add the PPO, which is this ratio here. But if we ignore them, it actually looks like the vanilla policy gradient quite similarly. But two differences are highlighted in red, which is this 1 over length and this divided by STD. So this is how we argue GRPO is biased in terms of the length and the question difficulty, because with this 1 over length, actually all the policy gradient is again reweighted by the response length of the response itself. This reweighting is harmful because in GRPO, we will optimize the model parameters using a lot of rollouts given a single question. These rollouts will have different lengths. And if we reweight the policy gradient using this length, for example, for correct responses, all these advantages will be positive values. And then the shorter the response is, the larger this reweighting is, then these positive gradients will be upweighted. So the overall optimization will be biased towards shorter but correct responses. And on the other hand, if the response is wrong, is incorrect, this advantage will be a negative value, which means for a longer response, actually this whole term, this reweighting term will be smaller. That means we will penalize less for the incorrect but longer responses. So in summary, these two, like for either for incorrect and correct responses, this 1 over length term will have opposite direction for the biased optimization, which is not what we want. And on the other hand, this dividing by STD term will introduce as a question level difficulty bias, because this reward vector, which is R, the reward for response 1, response G, will have smaller value for those easy or hard questions, because all this reward will look like very, very flat, like all 0 or nearly all 0 or nearly all 1. So that this standard deviation will be quite small. So dividing by this will even like upweight the overall weight of this policy gradient. So that is how GRPO itself has these two type of biases. And that is also why, especially for the lens bias, that is why people found if I use vanilla GRPO for optimization, we will have very weird response lens behavior. And for Docker GRPO, what we do is very simple. We just want to go back to the very basic but correct formulation of policy gradient. So we just remove these two bias term in red, and we hope to do GR correctly, or we call it GRPO downright.
Wow, that's amazing. That's truly even to the degree of unbelievable because, GRPO and DeepSeek was all the buzz during that time. I remember, when I opened the newspaper, it's even on the top of the news here. So why do you think they could make such like a bias error? Is it a remiss, or what do you think such bias isn't caught by the researchers?
Yeah, that's a great question. So when we look at the GRPO paper, which is the DeepSeek math paper, like in 2024, we also are quite curious why this happened in the first place. And one hypothesis from us is like, for example, for this advantage normalization, what they did is the typical normalization which we use in statistics, minus by the average and divided by the standard deviation. Perhaps they didn't really consider the biasness in terms of RA. And actually, empirically, I don't think this will cause a lot of issue until we really scale it up and we observe some strange phenomenon. But at that time, perhaps for their setting, it is fine empirically. And then for the 1/, length bias, I guess doing the average loss is a quite typical operation for many of the deep learning implementation or formulation. So it looks like if we sum over all the tokens, then we'd better divide it by the token, the length of the whole response or the number of tokens we have here. So that seems also reasonable from the very beginning, which the authors of GRPO raised these questions. But in fact, from the RL perspective, especially policy gradient, this is a biased one, but perhaps they didn't notice it until like this year.
For the audience who don't really have a very strong theoretical background, when they look at this algorithm, they may feel like this normalization makes intuitive sense because if you look at the inner loop, you are essentially weight the advantage of rollouts based on the sum of the relative probability. And what will happen is that for those rollouts that has longer tokens, it will kind of get a fairly large weight, even if the length should not really matter on the total loss. So what's wrong with such an intuitive understanding?
Yeah, great question. I think the part we might miss is that all these responses are sampled from our policy, because during this sampling and because RL is to optimize the expected reward, and this expected reward is over the state and the policy. Over the policy means we sample all the actions from the policy, and all these responses, either is shorter or longer, are all sampled from the policy. That means it will already have different sampling probability. Let's say for longer responses, we might expect the probability of this exact long response is smaller than another shorter response. And then in the expectation point of view, it's actually average out, right? Because sampling a longer response got smaller probability, and summing up a longer response got larger loss, but they will average out during this expectation process.
Got you. Just zoom out a bit on the whole reinforcement learning training algorithm design. How much of this is theoretical versus how much it is practical engineering? Because if we look at the GRPO or PPO algorithms, you have all this clipping and the KL divergence factor that are, I assume already biased to the original policy gradient, because, you have this very sharp clipping factor that have to be biased against those expectations. So there seems to already be a lot of practical and engineering factors coming into the place that people just find it useful, even if it's already biased. Does the bias and unbiased still matters if our training has already been polluted with these engineering issues?
Oh, got you. That's a really great question. It's very hard to be fully unbiased, I would say, especially when we take the engineering, the implementation into consideration. Let's say even even for the pure optimization point of view, we use, for example, FP16 or float BF16 is already a quantization of the a real value. It's also introduced some bias if we take that into consideration. But here, I think there are different levels of biases here. What I described just now is for the numerical biases is a very low level bias which we cannot control. But what we note here for the GRPO bias is at a very high level, which is incorrect theoretically, and we can fix it. And what you described just now for the clipping, the first order approximation of PPO, these kind of biases are something that we choose to trade off with the bias for the variance. So I think there are different levels, and what we hope to do is to fix the very high level and the theoretically incorrect biases to make it unbiased. But some other levels of biases, that is our design choice for the trade-off, or that is something that we cannot really control or fix, we will let it go, and it will not create very harmful results, unlike the GRPO bias, which will lead to like very bad response length issues.
If we further zoom out from reinforced learning to even the stage of pre-training or maybe mid-training or maybe a bit SFT, I think they also have somehow a similar problem of, when we are performing fine-tuning, those responses that are longer naturally, get more weight. And in the pre-training stages, people also try to balance the different distribution and of the data mixture. Do you think it's also something going on with the theoretical parts of this algorithm?
Yeah, I think it also depends on the granularity we model the granularity we model the data. So here in RL, the granularity is the response level. So we will treat each response as the action, and we decompose this macro action into a token level action by factorizing the probability. So that is how we need to sum up the log probability instead of doing the average. But for the pre-training stage, from what I understand, the granularity is typically on the token level. So we do the next token prediction. And in this sense, we just pack all the numbers into a fixed context window training batch. And then no matter we do the summation or average, it is fine because our context window is a fixed context window. If we sum it up, it's fine. If we divide by the length, it is a constant length. It won't introduce any bias here. So I guess the biases we are talking about here is very severe once we go into the RL stage and once we sample these responses and we do this kind of GRPO, this kind of contrastive learning here. These biases will emerge and will create very harmful results.
Amazing. Moving from Dr. GRPO to your next paper, defeating the training inference mismatch via FP16. So this paper makes all the buzz on Twitter. According to Andrej Karpathy on his tweet, it's all about your paper and Sydney Sweeney's books. And apparently your paper attracts more attention from Andrej Karpathy. So could you give us a high-level backstory of this paper?
Yeah, actually, this is a paper collaborated with few amazing colleagues here at CA Lab. And the backstory is that actually we were doing another project before this project, and we didn't even intend to focus on this problem before. We were doing another project, and during that project, the trainings always collapse. It's always unstable. We want to investigate why this happens, what causes this instability. And we narrowed down and we found this training inference mismatch matters a lot. And during that time, I think the first block, which is the truncated importance sampling block from UCSD, went out. And then we found this issue actually is quite relevant to what we found for the training instability. And we dig it deeper a bit, and we found actually precision matters a lot for this training inference mismatch. Simply switching from the BF16 to FP16 can resolve this mismatch issue to a large extent.
Awesome. So could you step back and walk through what FP16 versus BF16 is?
Oh yeah, maybe to most of us, FP16 is a very old technology because we are all by default using BF16. So basically they are all using 16-bit to represent the numbers in computers. But what's the difference is they allocate different amount of bits for exponent and mantissa. For FP16, they will allocate more bits for mantissa, which will lead to higher precision but smaller dynamic range for the values can be represented. And for BF16, it can have very high, very wide dynamic range but it will have less precision. And what we found here is precision matters more in RL training of LLMs than the dynamic range.
Could you give us like a very high level overview on the numerical stability in the field of maybe not only reinforcement learning, but also machine learning in general? Because I think numerical stability has been there quite a while. People has studied all different techniques like residual connections or for vanishing gradients before. Why is this still an unsolved problem?
Yeah, definitely. It has a very long history, and many researchers and engineers are tackling these numerical issues. And I guess that is also why this BF16 it happens. And for BF16, what we want is have a very large dynamic range while reducing the computation burden, because using FP32 is too heavy and too costly, and we want to have half precision training, but FP16 doesn't provide us enough dynamic range, and that's why we have BF16. So that is a history we went through for the past years, and that becomes a default. But here, I think what we want, what is different here is like for RL tuning of LLMs, the mismatch happens because we have very complex infrastructure for both rollout engine and training engine. So this is not an issue back several years ago where we don't really do large scale RL training on large models. We just do SFT training, supervised training, or on smaller scales models, and we don't have separate training and rollout engines. Yeah, so that is why this numerical issue come to the surface for these days, even though we have a long history of optimizing it.
Could you share with us why we have two different engines, even if the model parameters are essentially the same? Isn't that quite wasteful in terms of the GPU memory usage?
Yeah, I think it's mostly for efficiency consideration. Like, for example, in a typical AMRL training framework, we will have VeRL or SGLang as a rollout engine, which is highly optimized for the autoregressive generation. And then we will have, for example, Megatron as the SDP deep speed, and the training engine side, which is suitable for like different kind of parallelization, like acceleration kind of stuff. So we want to leverage both the good thing of both sides to combine together to get a highly optimized framework overall. So that is why we choose to separate the engines, and even more, we may do the asynchronous training, like we keep both engines busy, so that is to resolve the question you mentioned, like the different engines might occupy different GPU memories, but they are not wasteful because residing on different GPUs and having different memories, but they are all doing heavy amount of work. And all this throughput is very high.
So why is BF16 so popular before? Why people haven't used FP16 for all the different training tasks here? Is it because for reinforcement learning, I think we already trying to impose a lot of constraints on the model should not deviate too much from the current model. So the range will be small anyway, but we find that the discrepancy is larger. So we should always have a trade more precision over range. Or is there any other deeper reasons?
Yeah, that's a very great question. I think previously we use BF16 is to optimize from scratch, optimize the network from scratch. In that phase, I think the optimization landscape might be quite complex, and the values happened during the optimization might be quite large a range. That's how BF16 can help with this very large range optimization process. And after all this pre-training from scratch and mid-training, we have a quite stable parameter state, which where the values are quite like in a smaller range and quite stable. And for the RL process, we typically just fine-tune a little bit or even a sub-network of the whole model, and the parameters won't deviate too much. And here, what matters more is the training engines and different engines numerical mismatch. And by using FP16, we have smaller numerical mismatch. And this can give us more benefit compared to the larger dynamic range that BF16 offers us.
So is it correct that even if FP16 is better for reinforcement learning, for the other stage of the large range model training, let's say pre-training, mid-training, or even SFT, that I think you don't have two different engines, we should still stick with BF16 for its larger range? What would be your recommendation?
Yeah, I agree. I think what you propose is a quite reasonable procedure.
And how would the quantitization which trying to further save the GPU memory by representing floating point with integer interact with this precision discrepancy issue here?
Oh yeah, so first of all, we didn't try like FP8 or Int8 training yet, but I think the idea behind is similar. Whatever quantization or floating point or integer value representation we have, we will definitely have this training engine and inference engine mismatch. And we can fix it from algorithm side, like doing important sampling. This is what people are currently doing. This can fix to some extent, but we'd better like to fix this mismatch from the very beginning, from the root cause. And if we use some quantized training, we'd better also align the value representations on both sides to keep the mismatch small as possible to avoid any training instability during RL process.
Now, what do you think? Because we already have much stronger reasoning, math, and coding models before from frontier model here, and they probably should also face some similar issue here. What's your best guess? What are their solution to this problem before they even see your papers? Is it because larger model natively more less vulnerable to this discrepancy, or do you think they have us a better solution, or maybe they just use FP32 because they have more GPU to burn?
Yeah, I think frontier labs maybe if they don't use FP16 technology, maybe they already have some other technology that can reduce the mismatch already. So I guess frontier labs definitely have already fixed this numerical issue. And for the open source community, actually, most of the people observe instability issues. So the issue is there and it is not fixed. And to deliver a good model, we don't really need a fully stable training, I guess. Because whenever the training collapse, we can save the checkpoint and restart again. And we have various tricks and engineering methods to make the final model performant to deliver a good model that is good on benchmarks, but we may not solve the root cause of the training instability. That is my guess.
Okay, that's amazing. And given all the current issues with the reinforced learning, I know you have your own reinforced learning framework called OAT. Do you mind just share with us a bit backstory of OAT? Like, when do you start writing this framework? What problem does it solve? And what is the backstory behind it?
Oh yeah, sure. I guess nowadays there are more and more RL frameworks, and OAT is just a simple attempt for me to create my own and to fulfill some of my own research project. So I started coding OAT back in May of last year. That is when VeRL is not so popular and same as some of the other RL frameworks. I didn't intend to create a really large-scale RL frameworks, but instead I want to create a simple and hackable and user-friendly, lightweight framework, especially for single-node training, because I found most of the research, like the academia research, focus on single-node training, like less than 7B, 8B model parameters. I think that is enough. And I focus user-friendly more than scalability. And the start of the OAT development is from one of my online alignment projects where I want to implement online DPO. And at that time, I don't find any suitable framework to start. And because they either do not implement online DPO or the efficiency is too low. So that's why I decided to write my own, starting from online DPO and then later switch to online PPO and online PPO with verifiable reward. Those are very simple extension based on the first version of the framework.
That's amazing. How hard is it to write a framework from scratch? What's the technical challenges you have been faced? Could you share with us your a step-by-step building process you had?
Yeah, sure. So actually, I had a bit RL framework experience back in several years ago because I work on deep RL. It is very similar because the basic building block is just actor and learner. Actor is where the policy take actions given some observation. Learner is to sample from these experiences, this data buffer, and then optimize the network. And what we have next is to synchronize the weights from learner to actor. That completes the whole loop or of-field framework. And the component is already there, and I know this before. And what I need is to fill in these components with modern LLM infrastructure. So I put VLM as the actor, I put DeepSpeed as the learner, and we try to combine them together to make the fully loop working, runnable, and basically that is how. And during this process, I also refer to many amazing infrastructure work, for example, the GRPO, OpenRHF, and VeRL, of course, and DeepSpeed. And without this prior infrastructure works, I don't think it is possible for me to write the art for myself.
That's amazing. How would you compare art against VeRL? Because VeRL is kind of the current most popular reinforcement learning framework built by ByteDance and is backed up by a large industry. So if I'm a new reinforced learning researcher, I'm trying to pick different framework, what would you recommend?
Oh yeah, it's a hard question. I think comparison is relatively simple. I know VeRL is backed by a group of people, like full-time people perhaps, at ByteDance, and development is very fast, and then they incorporate many new technologies in a very timely manner. Compared to VeRL, I couldn't really maintain it as often as possible. So I think VeRL has many features, and it supports very large-scale multi-node training. It is more scalable, of course, but as a result, actually their code base is more complex as well. So typically, a new beginner will complain about VeRL's complexity, too many layers of abstractions, and very hard for them to customize some algorithms or some low-level stuff. And in that sense, Alt might be a more friendly beginning for the new joiners, because Alt has very clear modular component, and what you need is to write your sampling logic and then your training logic in different classes, and then combine them together. You have a training suite. And I think Alt and VeRL is not competitive like to each other. I don't think for the new beginner, I don't recommend either actually. I would like new beginners to first learn the overall concept and then pick some runnable scripts to feel the IO training first. And you need to look at the critical path of your code. Like for your runnable scripts, where does your rollout happen and where does your training happen? You need to locate those codes, and you will find very minimal critical paths out of a very large code base. And then what you need to focus is only on the critical path and do necessary modifications, and that is all. So choosing Alt or VeRL doesn't matter.
What do you mean by runnable script? Do you mean doing all this reinforcement training in a pretty offline fashion? We first load the rollout engine and all the model parameters, let the rollouts free the GPU memory, get onto the training engine, send the training data to it, free memory again. Is that the runnable script you were thinking about?
Yeah, something like that. I think there are some educational resource for IO training, but I can't remember the name. I strongly recommend new beginners to start from theirs.
Final question. What do you think would be the most important problems for large language model training? I want two answers. One is for the next 1 year, another is for the next 10 years.
Okay, that is a very broad question. Like for next 1 year. Disclaimer, I don't have a very definite answer for this, because LLM training, like many people, top researchers are working on it, and the future is very unpredictable. I think for me, very important problem is to creating good benchmarks. What we really want from LLMs. We know LLM is a very good technology. It impacts the society a lot. But what currently the frontier labs are pushing is to maximizing the benchmarks mostly. But are these benchmarks real enough for many real world tasks where human beings really facing? Perhaps not very closely. So creating a very realistic benchmarks is a high priority from my side, because benchmarks are also reward functions for either RIO of LLMs or RIO of our human beings. We also do the reward climbing. So creating a correct and realistic benchmark is quite high importance for me for the next few years. Yes.
What about 10 years?
10 years. Maybe for the whole community, figure out how we can leverage the power of LLMs to benefit our humanity, either do frontier scientific discovery or, I don't know, to save energy, to improve different levels of efficiency of the society. Yeah, it's more high level stuff that AI community as a whole need to think about, I think.
Dr. Zichen Liu, thank you so much for your time.
Thank you for having me.